Okay guys, so there are three things basically. One is population distribution. Second is sample distribution, or we call it sampling distribution. Third is sampling distribution of sample mean. Now let's say the population size is 20,000. Generally we don't know the population size if we are doing sampling. That's the whole point. Sampling distribution, let's say we are taking sample size of 100. This I'll come to later. This is basically, let's say we are taking 500 samples. 500 samples, not the size of the sample. Size of the sample is still 100. We are taking 500 samples. So population distribution is very simple and basic. Let's say it's a binomial distribution. So this becomes the mean of the population. This is standard deviation. So this is straightforward formulas, which is sigma I 1 to n xi over n variance xi minus mu square sigma I 1 to n over n, and sigma equal to under root of this full thing. That is straightforward. Now for sampling distribution with the size of 100, the mean of that sampling distribution need not be same as what we have here. This we know. This is like straightforward thing. So the data points we plotted, the 100 data points we plotted, somewhat came right skewed, something like this. Most of the data points here. This is the sampling mean. This is the sampling mean, the mean of the sample. And let's say the standard deviation is this, sigma s, right? Now the sampling deviation is sigma s, and this mu s is pretty simple. Let's say our data points here range from x1 to x100, and this x is different from the x here. The mu is simple, which is sigma I is equal to 1 to 100 xi over 100. Simple. Coming on to the point that the standard deviation of variance, let's say, is xi minus mu bar s, this mean. Now this is the whole point of what you are deducting. This is the mean, mu s over square over n minus 1. Now okay, now why this is n minus 1 here? This totally depends upon what you are trying to achieve. If you are trying to achieve, because we say that this is standard variation, this is standard deviation, variance tends to the actual standard deviation, right? In that case, if we want this to be tending to the actual population, in that case we take this. Else forget about this thing. Even though they are saying sample, but they are not asking us to predict anything. In that case, we are going to take a basic standard deviation, because if you see at the end of the day, it is just a normal graph which has 100 data points plotted. Now why this n minus 1? So I am going to take a smaller example for that. For example, there is a population. Now the population can have n number of points, right? There is a population whose mean is 20. Now this mean 20 of the population, it's pretty much straightforward that for each data point, if I do mean minus psi, which is, for example, I take 3 data points, 4 data points, whatever. So I take, let's say, 18, 32, 16. So this will be -2, 12 and 4, right? And likewise, now this population, if this population is for a very wide audience which we cannot estimate, that is why we go for sampling process. If we have a population with finite number of people, then why would we ever go for sampling? The whole point, we are going for sampling because we cannot collect data for full population. Now here, the basic rule is the sum of standard deviation of each point should be 0, right? This is an unending process. So that is why whenever we are going to estimate we are going to know the population mean, it is going to be n, because its standard deviation depends upon each and every data point. I'll come back to why I am saying each and every data point. For example, I come to sample and I am taking sample of, let's say, 4 size, right? We know this is, like they have given in the question, that the sample is of size 4. In that case, 1, 2, 3, 4, these are our 4 readings with data points, and they have given the sample is size 4 and mean is, here it was 20, so let's say I'll take 15 here. Now sample is size 4, mean is 15, and let's say my first reading is 10, second is 25, third is 35. So this xi minus mu s would be 5. 10 minus 15 minus 5, 20, 10, 20. Now, can you randomly put any value on the fourth value, or it has to be such that this deviation sums to 0 and the mean of all these values comes out to be 15? I guess the second point, you cannot put any random value on fourth. This value strictly depends upon the other 3 values. And even though you don't know this value, you can easily judge this value. So basically, for finding out the mean of a sample, we didn't actually need 4 values. With only 3 values, we can get this mean predicted by, we have the mean, we can predict the fourth value. Now, since for there is a slight conceptual difference, we call this as degree of freedom. So the degree of freedom for a sample is n-1, and for population, because the standard deviation or variance would always be sigma of I is equal to 1 to n xi minus mu over whole square over degrees of freedom. Now this degree of freedom in a population is always n, because with every second data point, as soon as we add one more, the mu is going to change and everything is going to change. But with sample size, if we have 100 samples of size 4 and we add one more data point to one of the samples, that doesn't make any sense, because that way we are going to create a bias in our theory to predict the population mean. So that is why for a sampling distribution, we take sigma square sigma I is equal to 1 to n xi minus mu s whole square over n minus 1. Now, if you can understand it in a second manner also. For example, forget about this xi minus mu. Now this mu s, depending upon whatever the sample we take, can be on this side, can be on this side as well. Very good if it is equal to mu, but can be here as well. Now, in order to make this variance tending towards this variance, we have to make sure that this value should tend towards this actual value. Now, since we know we are taking a square, so even though it's a smaller value or a bigger value, this whole value is going to come down x. So it's like 20 minus the mean of population is, let's say, 5. 20 minus the mean of sample is, let's say, 6. This is 15 square, this is 16 square. Now in order, what number should we divide the sample size with so that it actually comes to the tends towards this value? So this value is more than this, then that means the denominator should be less than what we have here. So n-1 was taken to counter this variance, that our sample variance should always tends toward the mean variance. To in order to counter that, they came up with n-1. That is a theoretical explanation to this. There is a mathematical proof which is not required, but just so that you guys know, this is how they do. They sample, the variance is always something over degree of freedom, and for a population, in case of a sample, and for population, it's basically divided by the total size, because that is the actual population. You only tell me, why would I go through all this hustle if I know each and everything about the population? If I know the size of the population, the mean of the population, and everything, data points of the population, I would never do sampling and sampling distribution. The whole point of creating sample is to predict population. So that is why these guys came up with the formulas which are rigged in such a way that they somehow points toward the population. Now coming on to the third thing, sampling distribution of sample mean, that I'll explain in next video.